extra. Wouldn't want to do that anyway, right? So, all right. Okay, just give me a minute. And um, okay, so that'll be the plan then. So 11 tomorrow we'll be here. We'll go through the next lab. Um, and this one will have AI content and will be on search. And the timing's perfect because we're just about to finish the all the normal non-game tree search algorithms today, I believe. And that's exactly what is covered on the next lab. So I'd hate to put it off another week. Um, other other administrative stuff. So the time change has been approved. So thanks for your help with that. So starting next week, Monday through Wednesday, we'll shift. And Thursday and Friday will be exactly as they've been. Over here, Monday through Wednesday will be 1100 on the other side of the dividing wall. And hopefully that'll be good for everyone. Okay. Fantastic. The homework, I didn't double check when it's set. It's probably still okay. I think I need an hour, 2 hours maybe to do game tree search, and then we're ready to, review homework and talk about the extra tests. And if we do need to delay the test further, we'll delay it, but then we need to start new material. So it'd be good if we can avoid that. When is the homework due? Can anyone see it on their next Wednesday? Um, yeah, that's probably fair. Um, let's see. Well, we could do so normally, I mean, we want to go through the homework. We want to have some time to go over the old tests. We could do that either as 1 hour or two. I think kind of 1 hour feels a little short, but two feels like overkill, like it would be really boring. I don't know what you think about that. When's good? Let's just talk about. I did warn you, so like, when would be a good day for a test? Should we shoot for end of next week, or beginning of the week after that? What should we shoot for? I know you don't even have the material yet, but it's still, this is life. We just have to make a schedule and try to stick to it.
I think it would just depend on the lab. Yeah, the homework lab and then a test to study for. I think that would help.
Okay, so the lab will go for 2 weeks this time. So actually, maybe trying to do the test like dead in the middle is not too bad. We could even do it on the Friday because we won't have a new lab next Friday. Is that good? Okay, so we'll shoot for the test next Friday at 11 over there. Oh, wait, no, Friday's here. Friday's here. All right. Okay, awesome. Easy, easy. All right, so let's dive in. Pens, a needle today. So this is where we are. Let's kind of circle the wagons a little bit. So if I said, okay, I'm very time sensitive in my application. I need results fast. That's what I care about. That's all I care about. What are you going to recommend to me in terms of algorithms? Again, assume my problems are hard. They're going to get big.
Bidirectional.
Bidirectional. Oh, but you know what? I can't invert the successor function. I have no way of knowing. When I have a state, I know where I'm going to, but I don't know how to what state I came from. So I can't do reverse. So therefore, I can't do bidirectional. So what do you tell me?
Iterative deepening.
Iterative deepening? Okay. Yeah. Or breadth first. If all I care about is and breadth first is nice and simple. That's really all I care about. That's fine. Okay, what if I'm the opposite way and this is going on some tiny CPU that goes in some micro UAV that's going to go over and needs to have a little bit of AI in it. I have no memory to speak of. What should I be? What do you want to recommend me? What's that?
Depth limited.
Depth limited? Oh, yeah, okay, but then I have to make that guess as to how deep to go.
If you don't have a guess, then depth first. But I think
Depth first?
you would do iterative deepening because I mean the M can go on forever.
What's the relationship between D and M? Which is bigger?
M.
Always. It's always at least as big as D. Okay, so yeah, iterative deepening probably. Again, you could have probably should have started out with bidirectional and wait for me to say, oh no, I still for that problem I also can't do reverse search. Okay, and if I just care about getting the cheapest solution, I mean, all we got right now is, run it a bunch of times, see if you could scramble things up a little bit. Maybe you'll get lucky and a better solution will bubble to the top. That's it. Okay, we're gonna fix that today, I hope. All right. All right, so this is informed search. That was blind search. This is informed search. Two more algorithms to go through. We can easily do that in one day. All right, so what is informed search? So again, what made blind search blind is it never knows. Even when it's right before the solution, it has no idea. It just has that goal test. If goal says false, that's what it knows. I'm not at a goal yet. Okay, now we're going to have some idea, some kind of estimate that might help us. Let's see. Okay, up till now, we have this, what was called the path cost. That's the incurred cost so far, which is a solid cost. If we actually know I'm going to fly to Boston and from there to Cleveland, I know the cost, the distance, anything, the time, anything I need to know. But this is a solid cost. Okay, but now we're going to assume we also have an estimate of the remaining cost. Now, here's the kicker. It's an estimate. Okay, not a solid cost. Okay, and then the logical estimate of the total cost once I have this would be, hey, just sum those things up. This is G, solid incurred cost. This is estimate of remaining cost, and that's usually called F. Everyone uses these variables, so I like consider that. You should know that. F is total, G is incurred, H is anticipated remaining cost. Okay, fair enough. All right, so let's see. Let's assume we're going to have that, and let's see what we can do with it. Okay, H, that variable H, the estimate of remaining cost, gets this name from the long English title it used to have, the heuristic function. Okay, heuristic just means guess, right? Or maybe a wise guess. Okay, right, as an estimate, don't rely on it. Okay, so now do note that H needs to be available for absolutely all states just to make our algorithm kind of flow smoothly. I need to be able to put that number on every state to be able to go do my algorithm. Okay, so let's do the easiest of the two algorithms, which is greedy search. Okay, greedy search just cares about the remaining cost, this H. Okay, these are the numbers. Now, if I do that, that means that once again, like with uniform cost, I need to keep the list sorted with the most attractive candidates toward the bottom. Okay, the cheapest ones, that's what I mean. Most attractive, cheapest, lowest numbers toward the bottom. Okay, now the idea here again is going to be we're going to search the node closest to the goal. That's the one with the lowest H. I mean, assuming H is good, first. Okay. Now, what can we rely on with these numbers? If you've got a good eye, you will note these are the same numbers as for the uniform cost slide because, again, we're thinking worst case. So worst case is obviously estimates are maybe going to be bad. Maybe we're going to assume they're very misleading. Okay, terribly misleading even in the worst case. Okay. All right. The algorithm still flows the same way as normal, right? Oh, the 9 should have been crossed out. Look at that. Didn't get crossed out. But, take a node, goal test it, get the successor function, get its children, check for circularity, check for, check for a loop, throw those children out, put the rest on the list while keeping the list sorted. All right. All right, so let's talk through this. Do we think this will give us the optimal solution first? If we get to a solution, a goal node, is that going to be the cheapest goal node?
I'm gonna say it depends on what your cost is. You used an example a couple of days ago where you were talking about searching for the bathroom, which is that, right?
Yeah.
So in this case, if I were like taking steps. And I'm going towards the bathroom, one of the greasers running into this wall.
Well, it might. Yeah, I mean, that's perspicacious. I mean, it will run you into the wall temporarily, and then the other children, right? If it's me in my starting position, right? Yeah, that was the one closest to the bathroom. If I used crow fly distance to the bathroom, right, which is sensible Euclidean distance, yes, I would go there first. That doesn't mean I'm stuck at the wall. I will then back up and try another location, but yeah, it sure ain't gonna help me. Okay, so what do you think? Is it a yes or a no on optimal solution? I mean, we want an algorithm that gives the optimal solution all the time first and never makes a mistake. What do you think?
Most of the times, be the best.
Most of the time, but that's means you don't think it's optimal. If there's any time when it doesn't give me the best first, it's not optimal. What's that? Okay, and I agree with that. I mean, it was again, the numbers, they're meant to be helpful, but replace them all by 3 million, because we're thinking worst case here. Okay. And probably you can do even worse than that in terms of assigning numbers, and probably we will in a minute. Okay, what's the computational complexity here? How much of the tree can you make me explore by deviously locating the solution and giving me bad estimates for my nodes?
Theoretically, all of it.
Theoretically, all of it. How would you do that?
Each of them.
Now, B to the M, yes, but I'm asking how would you do, like, how specifically where do I put the solution and how do I set up the costs to make things bad for the algorithm?
However, the cost worked out, you have
Yeah.
to be able to hide the solution behind the high cost.
There you go. Put the highest number as the parent to the best goal. Oh, as a parent to the goal. Just one goal node and hide it under a high cost node. It will search the whole tree, which is B to the M, as we said. Okay, so B to the M, not too great. Okay, what's the worst we can do in terms of loading up the processing list?
Yeah. As soon as you got to the bottom, you have to start taking notes off. You only ever have time.
You can only ever have B times then. Well, I mean, Brett's first had B to the D. So we can do worse than B times N.
Actually, now you could, because as soon as you got to the bottom, the next cheapest could be all that appear. That would go wrong.
Keep in mind, you got a lot of tools here. You can locate the node wherever you want it. You can mislead me with the cost, however you want to mislead me, because we're talking worst case. So how do you want to mislead me? This is similar to what we've done before, actually. That's good. We're looping back. Because this is a little, hopefully in the future you'll recognize this. We've already been here.
I think it's close to B.
B to the M. Okay. And how would it be B to the M?
All has the same value.
What's that?
All has the same value.
All have the same value? Then I don't know. It'll be up to the tiebreaker. You might get lucky and you might not load the thing at all.
Or you maybe unlucky and lost.
Or you may be unlucky, that's true. Maybe worst case, but with the tiebreaker. But I would like something even better. Can we make it have the same bad behavior as with, let's see, as uniform cost? That was actually where we've been here exactly before. Or just think of Brett's first kind of search, right? Remember where it ends up with a whole D layer on the processing list at one time, right?
So like you would want to put it all the way at the bottom.
Yeah.
Every branch above it, the path of the solution needs to be the worst option that you most confident on.
It's a little abstract for my brain this afternoon. You guys were better before, but I think it's because you've seen these nice algorithms with depth first and the derivative deepening, and you forgot. Okay, remember what we did before? We actually, if you do this, if you say make these cost 1, and these all cost 2, and these all cost 3, okay, and then we're going to hide the solution, and then I'm going to force you to go all the way down to M, and I'm going to make you put the whole bottom row, because they all cost more than the row above, so all those children will go and sit on the processing list at one time. So it will be about B to the M, not exactly B to the M, just a tiny bit less. You remember that? Is it good? Questions? Okay, think about this. This shouldn't be mysterious because you've seen it before. Okay, so yeah, we can force you to get the whole bottom of the trade much deeper than the shallow solution, all the way to the bottom. And let's just real quickly draw it. Right. The idea is, right, this one's one, cost one, these are cost two, these are cost three. Okay. Three. But this one is 3 million. And then under here is my cheap solution node. Right? That's the only solution node. And then we go on, and these are all fours, and etc. all the way on down. So it comes down, it's not going to go here. It's going to go and it's going to process all of these first, and the ones in the bottom row, which are all going to be cost M, are all going to end up on the processing list at one time. So it's essentially B to the M, except for this subtree is not going to be there, but that's really, it's not going to change the complexity. Better? Okay. All right. So let's see. All right. So again, greedy search, which unlike uniform cost, I think I've seen like once in my career actually used for something. Greedy search you see all the time, all the time. Okay. But on paper, in the worst case, it's the same. It's terrible. Now, I built some examples here, but I almost didn't need it thanks to Nick's comment there, because some of these have the same nature, just to kind of show how greedy search gets misled, right? So if you look here, starting from this node, like which child are we going to go to first? Okay, we're going to go to the one up top. Yeah, because it's the, well, hang on. What?
No, I meant like that.
Oh, I'm going the wrong way. Going the wrong way. Okay. As I thought, my brain's not quite working today. Okay, we're at this node. We're going to either this one or this one. Which one are we going to go to first? The right one, assuming we're using crowflies distance, right? Euclidean distance as our estimate of remaining cost, because this one looks closer to the solution. But as with going to the bathroom, trying to go through the partition wall, you're not actually going to get there that way, right? So you're going to waste computation. I can make this arbitrarily ugly here and make you waste any amount of time doing things that are totally hopeless. Okay, and then over here, would we rather take this node or would we rather take this node? If we're greedy, sir.
The second thing.
The second node. Okay, is this a better solution than this one? At least they both get to a solution. Well, so will this actually. Okay, which solution is cheaper?
If your cost is distance, the shorter one.
Yeah. So this shows you how it gets misled. It doesn't care about incurred costs. It's just leaving incurred costs on the side. So it says, well, the remaining cost is less here, therefore it must be better. So we're going there. All right. So where does that leave us? Well, okay, so we had one algorithm that only looks at the incurred cost, at G, and is terrible. And we have another one that only looks at the remaining cost and is terrible. Here's a thought. Let's use both of the costs. Let's combine them into the combined cost traditionally called F. And let's see if we can use that instead. Sounds reasonable?
Yes.
All right. Okay. So here we go. It's A star search. But again, we do need to, for right now, we're going to need to assume that H could be misleading. It is still an estimate. G is always solid, but H is misleading. Okay, so if H is misleading, what do we know about F? Is F solid? If H is a guess, F's also a guess, right? Okay, so that's could be an issue. Let's see. Okay. Again, this is the same picture because it's just a bunch of numbers, and we do the same thing. The only point of the numbers is that when nodes go on the processing list, the small ones go on the bottom. I mean, that's it. That's how the numbers affect things. Okay. So given that, is this going to be an optimal algorithm? It's the same situation that we've been in twice before. We have arbitrary numbers. They're really arbitrary. This is solid, but I can just adjust my H's to be the negative of whatever the G is plus whatever random thing I want to give you to mislead you. then that's the worst case. So that means F's are arbitrary worst case. So it's not going to be optimal. It's still not going to be optimal. What about the computation complexity?
You could still create the same situations that we had with the last.
Yes, you can. And so therefore we would have
BDM.
b to the m. We can hide the solution, do the same trick, and force you to go to the bottom of the tree. And memory complexity?
So
B to the m. Okay, so it's a trifecta. We have three algorithms that try to use quantitative data to guide the search, and three terrible outcomes. All right. Great. So where's our optimal algorithm? Well, actually, A star can be optimal, but you have to put some more constraints on it. So let's start talking about that. And then we're going to try to prove that it really will be optimal with those constraints. All right. Okay, but before we do that, this link supposedly should take us somewhere helpful. Let's see.
all of the other algorithms see the names hinted at what it is. Why is this one called base?
Oh, there's a long story to that. I don't remember it anymore. They were using letters, and there was a B and a C as well. I'd have to go back. ASAR was actually a big deal when it was invented. People did struggle with this quite a lot before they realized what was necessary to do. Okay, now this is a little bit. Okay, that should be a little more legible. Okay, if you click on that link, this is wonderful page of JavaScript code that I wrote that sits on my site. And I recommend it to you for use if you want to practice A star, or it is the most complicated of all the algorithms because you have the most to keep track of. It's always on the test. It's the most important for a simulationist of the search algorithms. So here's what it is. This is my map with my nodes creatively named A through I. A is always a start state. That whatever one is dark is the goal state. And what you see are the incremental costs to traverse. So that's time or distance, whatever you prefer. Think of it however you want. If you go from A to D is 1, from to A to B is 4. Okay, and so we ought to be able to go down here. Let's see if we can do the search, right? So we start with, on the processing list over here, we start with the state A, okay? What are its costs? What's the incurred cost when we start? We're sitting at state A, the initial state. What have we incurred? Zero. All right, what's the remaining cost? Okay, remaining costs are, indicated on each node. That's the, they're pretty random, but that's okay. For practicing the algorithm, random is actually the hardest. So, okay, so it's 8 here. Okay, so what would the F cost be? 8. 8 plus 0, it's going to be 8. Okay, so we're going to have our A over here with, I'll just put the F cost over in. No, that's what I ask you to do usually. H equals 8. F equals 8. That's our first node. Okay, right. Goal test it, not a goal node. Apply the successor function. Okay, what nodes do I get back from the successor function?
D and B and D.
Okay, B and D. This one's gone. Okay. Now they're going to end up in the wrong order. So sorry about that. Actually, what I'm going to do is I'm going to do what you should probably do when you do this. Forget about the processing list for this one, unless you want to deal with some frustration, or get a big piece of paper, kind of just put things in the middle so you always have room above and below everything. That's what you'd have to do if you really want to pursue that. So I'll leave that. Let's just say, let's put them right here. Let's take this one. This one got taken off, right? And we have B and D. Okay. All right. So the B node, what's the G cost for B? The incurred cost. 4. Remaining cost. 1. Yeah, I can add 4 plus 1. That's 5. Okay. For G, incurred cost. 1. 2. And 2. Total is 3. Okay, which one are we going to next? D. Okay, going to D next. Great. All right, so this one comes off the processing list. Is it a goal node? No, it's not. Let's apply the successor function. Okay, it's going to give us back A. We know not to bother with A. The similarity is going to kick it out. So as human simulators, if you coded it it would be wrong not to return A, but we don't want to waste our precious time learning, going around in circles that we know are going to happen. So let's not go to A. Okay, so E and G would be the children, right? All right. So the E node will have what as the incurred cost? Okay. So it gets 3 more, go from D to E. So what's the total incurred cost? It was already 1 previous, so you got to add that in. So it's 4. Okay, the remaining cost is 12. Okay. So that F is 60. Okay, and for G, the incurred cost is what? 5, or plus the 1 we already had. Okay, remaining cost 4, and F is 9. Okay, which is going to be the next node of the processing. Okay, it's going to be B. Okay, you see how you can use this, right? To actually go, and this is the kind of way that seems like it's maybe a lot to draw, but I do ask for all of that. Do the test questions, so it's a good way to test. Okay, and what you can do is you can come over here, and after each point, we didn't do this, but you could go and say, okay, what's going to happen next? Boom. Okay, the agenda A is gone from the agenda. B and D are now on the agenda. That's the processing list, if you didn't guess. This is the search tree with the 1 indicating A was the first node to be placed there. You with me? The only strange thing that needs explaining is the par here is the parent node. Okay, like if we actually were implementing A star, which we're not going to do, including tomorrow in the lab, we're not going to do it. It's a little much, but this just tells you that node 0, ID 0, is the parent node. So you can look over here, wherever you see the node, you can see what its parent node is, and that lets you reconstruct the whole path. Okay, great. So that's what we did, right? We had B and D, and then we said that D was going to be the next one off. Sure enough, it is the next one off. G and E are there. You can check all the data, right? And you can do as much or as little of this. I mean, I'm not asking you to waste your time, but you can just, the beauty of this is that you can go, the problem, some of them are easy, some of them are hard. This is actually a pretty easy one. These can actually be surprisingly difficult sometimes. If you refresh the page, you get a completely different problem, and you can just knock yourself out. You know, you can have plenty of practice. Make sure you should basically be perfect by the time you're done, and I'm sure you all will be, or you can be anyway. Itai.
Said H is a random number.
I think it is some kind of random number. Yeah.
How it's been defined?
How is what defined?
How is H defined? The G is there.
Well, it's what the computer is being told is this is the estimate of how much more cost it's going to be before you get to the solution. Right? That's what it's being told. And then when you get to the actual solution, you realize, oh, like here, right? The actual solution, you can get there in 4, right? A to B, B to E is 4, but this one thinks it's 9. To get there, this one thinks it's 1. Right? It's just random. It's good for exercise with the algorithm, but there would be you hope for a better heuristic function than that, a better H.
We need to calculate it, or it's being
No, it's provided to you. Yeah. Any other questions? All right. Okay. So now you can do most of the things in the, by the way, in the homework, so you can get going on that. If there's any game tree stuff, that's going to have to wait till next week. Advanced heuristic stuff, maybe by the end of the hour. All right, let's keep going. Oh, this is a traditional example. I don't do it anymore because I think it's better to use the tool that you can actually go and get arbitrary much data from. Okay. ASAR, in fact, can be an optimal algorithm. I claim, but I'll prove it by the end of the year. Don't believe it until it's been proven. Okay, I claim it's optimal. That is, it will always return the lowest cost solution first when H is admissible and sane. There are 2 conditions. The one that's always in every textbook I've seen is admissibility, but without the sanity. So apparently the textbook authors think it's so obvious that you'll see what I mean by sanity in a minute. That was so obvious that of course you would know that, and it's not. This is math. To prove it, you need to have all the assumptions. So you need both of those things: admissibility and sanity. Okay. All right. So that's a claim. which you should believe when it's proven to you. Okay, and but I'll make another claim that I'm not going to prove to you, but there's a reference here if you want to read it. In fact, what you can show about A star that is doesn't not only the case that if you configure it properly after you run, when it gives you a solution, you can be confident, 100% confident that is the best solution. There's no one else, no better solution out there. Not only that, you can show that there is no other algorithm that's also optimal and which is guaranteed to expand fewer nodes. Well, that's our surrogate for computation. So there's no faster algorithm in general. Okay. Now notice the careful wording here. There are other algorithms that might be faster on one specific problem, but if you take the whole space of problems, there's going to be no replacement for A star that AI students are going to learn 100 years from now. They'll be like, oh, this is always better than A star. There's no such thing, and it can be proven. Okay, but that proof is not one I would want to do in front of a class. I don't think it's easy. Okay, but let's focus on the first one. Okay. First, I got to tell you what those assumptions are that you need. Okay. So it's admissible if H never overestimates the remaining cost, which is a really weird condition. You should not underestimate how hard it will be to get this into your head so you don't make mistakes. Okay, because we're used to estimates that are, you try to be on the nose, you know you're not going to be on the nose, but any normal good estimate, if you're really trying to be on the nose, sometimes you should be high and sometimes you should be low. It should basically be balanced, right? You want to take like your uncertainty and kind of like center it around the solution. Okay, not for A star. If you have an H that ever overestimates the remaining cost, then you're not going to be optimal. Then you will risk getting a poor solution. It will say this is a solution, and maybe it will be a solution, but it won't be the best one. Okay, so this is very strange. So we think of this as H being very optimistic. H is very optimistic about the remaining cost. Well, being dead on is fine. If you could make an H that's dead on, but normally you can't. If you know you can't be perfect, you're gonna make a mistake, then make the mistake on the lowest. That's what it is. Now, these H functions do not fall from the sky. They have to be created for every application of A star that there is by whoever is doing the implementing or whoever is directing the implementers. And it could be you. So, yeah. So think about that. Okay, now the other thing I need in order to complete this proof is that H must also be sane. What do I mean by sane? Well, H needs to be 0 on goal nodes. Well, duh. I'm at the goal node. What's the estimate to the goal node? Should be 0, right? So no, not a lot of content there, but you do need to state that. All right, this is a little less obvious. H needs to be such that F is non-decreasing from parent to child, right? When I go to this, from this F to this F, oh, well, let's see, wait, what am I doing here? F should be non-decreasing, yeah. When I go from this F to this F, it should be non-decreasing. Now this does not obey that because the H's are random. Oh gosh, I'm sorry. All right. Now, if we have an H, which is not such that the F costs are non-decreasing, it's easy to fix it so that they are non-decreasing in the following way. Let's say I have a node and it has a particular estimate of remaining cost, which of course I can combine that with the incurred cost and get an estimate of the total cost. And then it has a child, which has its own estimate. Okay, and it is decreasing. The child has a lower estimate. There's an obvious way to fix it. So let's just think about this for a minute. Let's say you're working with a couple different contractors. This is just but this is like a math problem, not like a real world personality problem. A couple different theoretical contractors who always lowball you. They always say it's going to cost this amount, and when they're done, it's always more. The actual bill is always more. It is never less. Okay. All right, and you have a job, and you go to one guy, and you say, "Oh, that's gonna be $1,500 to do that job." Okay, and you go to the second guy. Okay, what do you say? Well, how much is it going to be to finish this job? He says, "Well, it's $1,700." Okay, so what do we know about the actual cost of the job? Yep, that's it. Now, when you have two estimates that you know are both low, the bigger one's always more accurate. Does that make sense? Okay, and therefore, if we have a situation like this, f is 8 going down to 3, we can simply correct this and up it to the larger number. Because we know that's already still can only be low. It might be dead on. Okay, or it might be low. It's not going to be high. So that's it. That's the solution as outlined on the next slide, but I think I talked through it enough. Now there's a name for this track. The name's not so important, but understanding it is really important. All right, so now let's see if we can prove that A star is optimal if our H is admissible and saying admissible, optimistic, and then the additional conditions. Okay, so I want to do this. I want to do this proof like follows. So I'd say this is the initial node. So the children. Okay, and then somewhere down here is the cheapest solution. Well, this is a solution node, right? So this would normally be black the way I write it. Cheapest solution. Okay, N0 is what I'm calling it. Okay, now how can we prove this? Okay, I want to prove it by contradiction. Okay, so what do I need to do?
Me too, you assume something. And then
Yeah.
See if you run into a problem.
Okay, all right, yeah, that sort of matches it. Okay, let's assume, what do we need to assume? If I want to show that it's optimal, I have to, and that's always optimal, I have to assume that, you know what happened? I have a validly coded A star algorithm, and I ran it. And you know what? I didn't get this solution. I got this other one down here called N1. And you know what? And I'm out of ink already for the day. Great. The cost of N1 is greater than f of N0. That's what happened. Okay, now proof by contradiction, you know how this works. So you make your key assumption. Now what I need to show now is that's not possible. If that happened, like all of math is broken. That's dramatic, but that's how we do it. Okay. All right. So let's think about this. Okay. So somehow we ran a valid A star. That means we put this node on the processing list and we did our normal rigmarole. Okay. And we got down to this one. And then this was the node that was on the bottom. We drew it, we goal tested it. Okay. And so where was this node? Did we fumble it through our hands? No, I mean not with a valid A star. So where would this node? Where is this node?
You haven't gone to it, or so.
You haven't gone through it. So where is it? It either doesn't exist, didn't go on the processing list at all, or one of its ancestors must be on the processing list, right? And there's no way that starting from here and always putting children on, that this node is not on the processing list, and also none of its ancestors are on the processing list. That's impossible. We always start off with an ancestor of this node on the processing list, and that should always be maintained. So let's call that ancestor N star. Okay. Now, due to the fact that we're going to have the cost be non-decreasing, what do we know about the cost of N star?
Smaller than the cost of N0.
Smaller or the same? Either way. Okay. All right. Okay, and then can we put these things together? F of N1 is greater than F of N0. F of N0 is greater than equal to F of N star. So putting those together, transitivity, right? Here to here, here to here. We know that F of N1 must therefore be strictly greater than F of N star. Right? Oh, so this node that we drew from the list has a greater cost than this other node that was on the list, and the list is sorted, so the cheapest node is on the bottom. Okay, that's impossible. And that's the proof for A star optimality. So it has a little bit of an unsatisfying feel to it, like all proofs by contradictions, but it's a perfectly valid proof. And hopefully you followed. Any questions? I won't be asking you to prove stuff, but at the same time, as you look at this and say, you see, it's not all that bad to understand what's going on here. All right. All right. So let's see what else we need to say in the last 7 minutes here. If I don't finish, it's fine, but that's most of the key stuff. Now, what I want to talk about, though, I still have some more stuff. It's important to the test. It's on the homework. It's always on the test as well, which is just making you think as deeply as I can about heuristic functions. Because it isn't really easy. Like I say, they don't grow on trees. Someone has to create them, and it kind of sucks to create them because there's no general rule. I can't give you an algorithm for building a validation function. You've got to understand your domain, and come up with a formula, with a function that can return an estimate that's always going to be, if it's going to make a mistake, it's going to be low. All right. All right. Now, let's see if we can follow what's on this slide. Obviously, if H were perfectly accurate, the number of nodes searched would just be the depth of the best solution. The total number of nodes searched would just be D. You believe that?
Just say it again, sorry.
So if H were perfectly accurate, the number of nodes searched that come off the processing list would just be D. Basically, we'd make a beeline down to the best solution.
That's logical.
Yeah, because all the other nodes would have worse numbers on them. They will all go to the back. The best node will always be the bottom. We'll just go boop, 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 boop. We'll just go right down the chain to the best solution. No false turnings. Okay, equally obvious, and we've done this today. If H is terrible, the worst case is we have to search the entire graph, which is B to the M. Okay, that's quite a range. Okay, now in practice, what people find is that the number of nodes searched grows exponentially with the graph size. Slower than B to the M. It's not quite that bad, but on average, it still is exponential. But the good news is you can make it a much better exponential. And you might be thinking, well, it's exponential. That's pretty bad. Yeah, but it's going to make a huge difference to get a better exponential, as you're going to see in a moment. Now, you can avoid it if your H is very, very accurate, right? If it's dead on, we already know life's going to be beautiful, but who can get dead on? Okay, in fact, if you can meet this criterion, okay, look, you've got to get within your average error in your H function has to be like the log of the size of the H function. That's not right. Log of 10 is 1, log of 100 is 2, right? Assuming base 10, right? That doesn't give you a lot of wiggle room. You've got to be quite accurate. And so don't bet on getting sub-exponential behavior from A star, but you can get a better exponential behavior. Let me show you an example on a problem you know and love, the 8 puzzle. So let's consider 2 heuristics for the 8 puzzle. Okay, 2 different H puzzles, right? Obviously, this is not path planning, and saying line of flight, measure the line of flight, measure the Euclidean distance is ridiculous here. That's not has nothing to do with this problem. We need something that relates to the problem. So H1 is going to be just count the number of tiles that are in the wrong position. First of all, do you agree that that is an actual admissible heuristic, that it will always be correct or low and never high? Is there any way H1 could be high? If a tile's out of position, you got to move it at least once, right? So this is probably going to be way, way low, but it's admissible.
Yeah.
Okay, well, let's compare H2. So H2 is the sum of the Manhattan distance. You know Manhattan distance? L1 distance? See some nods, but not 100% nods. That's Manhattan distance is the taxi cab distance in a city with a downtown grid, right? You can never cut across the blocks. You always have to go over and up, right? So to get the taxi cab distance between 2 points, it's the amount of over you have to do plus the amount of up you have to do. Okay, and of course with these tiles, that's exactly how they work. We can't cut the corner here. We've got to do 2 moves to get between those 2 locations. Okay. All right. So again, is this an admissible heuristic for this problem?
Yes.
Yeah, because you got to traverse that distance. The problem is, this is still going to be crazy optimistic because there's going to be tiles in our way, and it's going to take additional moves to get them out of the way to actually move the tile we want to move. Okay, they're both optimistic. Which one's better? Which heuristic is better?
H2.
H2, right? This is always going to be at least as big as this one. So this is our case of our two not quite so honest contractors, right? But H2 will always be better because it's bigger. There are two admissible heuristics and one's bigger. We know it's better. All right, so let's use this to study. Does it matter? Should we put effort into H? It's not easy to get good H functions. Let's think about it. Okay, so here we go. These numbers weren't generated by me, but they're the 8 puzzle. They went and put the solution at various steps, basically start from the solution and do D moves to like mess it up, right? Here you can mess it up only a tiny bit, 2 moves. Here, 22, that's quite a bit of messing up. Okay? And we solved it. First way is by iterative deepening search. This is the number of moves it takes the number of search nodes that actually need to be processed. 3 million, a little more. Okay, and these are the numbers with H1, and these are the numbers with H2. Which would you rather have? Okay, now anyone can look at that and say, I like that number. It's more than 10 times. I like this number. It's more than 10 times less than that one, right? All right, but I think this is a case where you really want to see it visually. If you just take those numbers, put them in Excel, say, build me a plot. This is that table of numbers. Okay, this is iterative deepening going off to space. Okay, and you see the other two look identical and they almost look like a flat line. You can't see any structure. That's how different. They're all exponentials, but that's how different exponentials are from one another. And then if you drop IDS out and say to Excel, plot it again. Sorry that the colors got confused, but here's the worst heuristic. Again, going off to space, while the best one is hardly budging from y equals 0. Okay, so what do you think? Does it matter if the heuristic is good? It totally matters. Okay, so yeah, so it'll probably be frustrating going through the material in the homework / old tests, but yep, do the best you can with it. Perfection isn't the bar here, but we want to engage seriously with it. Now, you give me 1 minute, 2 minutes to talk through this because this is the last slide, and this will let you also unlock these problems where you have to design stuff. This is the best I could do for you. Like I said, I don't have an algorithm to give you. Just follow these steps and you'll get a good H function. I don't have that. Okay, but this is the closest to that I have. Okay, so this is called the rule weakening approach to generating H functions. Okay, so let me show you how this works with an example applying it to the 8 puzzle. I can't guarantee this will apply to just every puzzle or every problem domain. It probably does not. Okay, but take a look. So for the 8 puzzle, you could say the rules of moving the tiles are, from A, tile can move from A, tile can move from square A to square B. Okay, if I want to move a tile from square A to square B, then A needs to be adjacent to B, and B needs to be blank. Fair enough, right? So if you formulate the rules of your domain like this, then you could think, well, maybe I can drop some of those rules out. If I drop it out, that should make the puzzle easier, so we should all get optimistic solutions, okay? And the hope is that, and hopefully the other thing about a good H function is it needs to be pretty easy to compute. When you're creating your own, don't think of, if you're writing like nested loops and stuff to like estimate remaining H cost, that's going to be a bad H function. It's probably going to be, you're probably trying to do like the whole search in your H function. That's not what we want. We want something relatively simple, okay? All right. So if I say this, let's change the rules to a tile can move from A to B if A is adjacent to B. Nothing about B being blank. So basically, I allow you to stack tiles. Okay? All right. Is it easy to estimate the remaining cost in that case?
Yes,
And what would it be?
the Manhattan distance.
It would be the Manhattan distance for each tile from where it is to where it's going. Okay? And if I drop the other condition, a tile can move from square A to square B if B is blank. Well, that basically lets me teleport tiles wherever I want. Okay. What is that? Does that sound familiar? Basically, I just need the blank to be over one solution tile, and I'll teleport the tile to its the one that belongs there, right there, which will leave a gap where another tile goes, and I'll teleport that one in. That look familiar? That's the H1 estimate from the last slide. And then you could possibly even drop both up. Okay, so this is not a lot, but at least it's something. Maybe it'll get you started down the right path as you're faced with a problem. I would say I'm done. But the worst I would say about those problems is, but this is always the case, you need to think about the domain first as step one, which is a pain for classroom purposes because that's a relatively large thing to put into a problem. So for each of the problems that's like this, you will see it makes you think about some new domain. If it's not a new domain, then you probably know the answer already. So what would be the point of asking? So yeah, try to be patient and take something good from the experience. It's probably the worst thing I have to ask you on test one. Okay. All right, cool. See you tomorrow, and we'll hopefully ramp up lab one.